Hi, we are the team from North Carolina State University, and our project was focusing on the Siler City resource recovery, facility expansion, and upgrade. I'm Silvana.
My name's Drew.
My name's Kai.
And I'm Kai Tanner. All right, so I'm going to walk you through the outline of our project. So first, we're going to give a brief background and general introduction. Then we'll go through some details on the plant expansion and all the permits associated with that. Then we'll go through the current process in the existing plant. And after we'll walk through how we decided the best alternatives for the expansion. And then finally, we'll look at the final design, our cost analysis, our sustainability review, and other necessary upgrades outside of our scope. So here is an aerial view of the current Siler City wastewater treatment plant. It's an activated sludge wastewater treatment plant, and you can see the two oxidation ditches in the bottom side of this image. There will be an increased demand caused by 2 new commercial sites, and so it'll go from 4 to 6 MGD in the coming years. The main focus of our project was on the new nitrogen limit. So they used to only have an ammonia limit for this plant, but the new permits associated with the upgrade are now regulating nitrogen. All right, so I'm going to now reiterate the scope of our work. And so we are focusing on the biological nutrient removal process, BNR process. And so we're going to be focusing on the removal of total nitrogen. We're focusing on the increased flow associated with those 2 new commercial sites and the construction and sequencing surrounding the BNR process specifically. So next, we are looking at the increased flow projections on this chart here. You can see on the left axis is the flow in MGDs. The bottom axis is the years. Baseline is blue, so that's just due to population increase. Above that is increased flow from a new chicken processing plant. And then above that is from a new advanced manufacturing facility. And as you can see from the chart, it's looking like in the year 2020, this year, the plant is expected to be at its current capacity, which is indicated by the bottom red line, if these new plants started operating today. And the top line is our expansion flow peak. So that is what we're trying to expand to. So next, you can see the new regulations we're working with. I'm sorry, these are the current regulations. So as you can see, there is currently only a total nitrogen load, which equates roughly to about 20 milligrams per liter. The new total nitrogen limit will be set at less than 3 milligrams per liter. So it's a huge decrease we're having to work with. And so, yeah, that's the main regulation we're going to be focusing on in the scope of our project. So next, you can now see the existing plant process. We highlighted our scope of work in red, and you can see, so there is some upstream stuff that goes through a grit screen with grit removal, the pump station. There's some equalization basins. What we're focusing on is expanding those oxidation ditches, which is where the main nutrient removal comes from. Right now it's fed by one blower C, as you can see on the schematic, and then there's a lime and alum addition box with some flocculate and clarifiers at the end. And then there's some downstream sludge processing stuff we won't be focusing on. With that, I'm going to pass it on to the other Kai, and he will walk you through our decision matrix for selecting the alternative.
The 3 best alternatives for upgrading the plant so it will meet its new permit limits are listed in this decision matrix. And they were scored based on construction footprint, cost, nutrient removal effectiveness, operator familiarity, and ease of implementation. And our highest scoring alternative, our best option, is the 5-stage BardenPHO process. And implementing it in this wastewater treatment plant will involve the construction of new basins around the existing oxidation ditches. More specifically, the plant will be upsized from 2 trains to where already there's 2 trains with the 2 oxidation ditches. So the new pre-anaerobic, pre-anoxic, post-anoxic, and re-aeration zones will all be new, and we'll be able to create 3 trains for this new flow and new nutrient removal limit. Doing this will enhance just the oxidation ditches, where currently nitrogen is in the form of ammonia is being metabolized into nitrites and nitrates, but still showing up in the effluent wastewater, making the total nitrogen too high for the limit. So the addition of anaerobic and anoxic areas will allow that nitrite and nitrate to be removed as nitrogen gas. The addition of this process will also be able to remove phosphorus biologically, where anaerobic zones make phosphorus available as phosphates. Those phosphates then enter oxidation ditches where they're uptaken and settled out in flocculating clarifiers. Currently, they just use lime and alum addition to help flocculate phosphorus, so this will be an added benefit to adding this process to what's going on right now. So we used Hydromantis GPSX software to model the current process of the plant. Doing this was crucial because we're choosing to build around the existing oxidation ditches and clarifiers. So we needed to calibrate structures in this software to match the process that's going on at Siler City. We did this by using historical data from influent and effluent wastewater, along with the dimensions of the oxidation ditch, the hydraulic retention time, the flow rate, and the dimensions of the clarifier too. We were able to manipulate dissolved oxygen levels in the oxidation ditch to match what the effluent was showing up as historically. And this graph shows that. As you can see, the total nitrogen is way above what the limit's going to be at 3 milligrams per liter. So something definitely needs to be done. Using the sizes of the existing oxidation ditches, along with the limited construction footprint of the area, and these formulas, we're able to size the additional basins around the oxidation ditches appropriately. And with these values, we put them into the Hydromantis GPSX model and built them around what we had as the oxidation ditch and the clarifiers. Manipulating the dissolved oxygen was what made these basins unique, because anaerobic, pre-anoxic, and post-anoxic have very little to no dissolved oxygen. We were able to find out that the diffused air grids are crucial in this process for upgrading the plant because they're what's going to be able to manipulate dissolved oxygen. We found with this model that it could reduce the total nitrogen from influent coming in, as you see here, down to below 3 milligrams per liter. But to do this, the aeration systems need to be upgraded at this plant. The volumes and hydraulic retention times hold up, but it is stressed that the blower system needs to be upgraded. And this graph just shows how we were able to reduce the total nitrogen below 3 milligrams per liter versus how it's currently operating. Total suspended solids and total phosphorus are high in this graph because the model that we built did not include the filters. The plant has not had problems with flocculating and filtering out total suspended solids and total phosphorus before, so it shouldn't be looked at with much concern in this graph. The star of the show is total nitrogen. So on the next slide, Drew's going to talk about the new air requirements of the plant to meet these nutrient limits.
So using the model, along with literature review, we were able to come up with airflow requirements that would help drive the 5-stage BardenPHO process. As Kai spoke earlier, the plant currently uses blower area staging area C to feed their oxidation ditches. We quickly found out that that would not provide the capacity needed for the upgrades to the BNR process. So we began with the equation at the bottom of the screen and found oxygen transfer rates and efficiencies based on literature review. Used the flow of wastewater through the plant, which would be the new 6 MGD capacity, along with BOD and ammonia levels that were given from the output of our model to find out what the air requirement would be for the ditches and the re-aeration tanks. We upsized those by 10%, about 10%, to get the blower capacity that would be required for the plant as a whole. Moving on to the next slide, we began creating a hydraulic grade line for the existing plant, and then here the upgraded plant. We looked at minor losses and major losses to come up with one pipe upsizing that would be required from the influent pump station all the way back up to the head of the BNR process. Moving on to the next slide, the plan view of the plant as it currently sits. On the far left side is where the influent wastewater enters the plant. There's a head workstation with grit removal and a fine bar screen before the wastewater travels to the influent pump station, which is the white roofed building on the left side. From there, wastewater is pumped all the way up the hill to the oxidation ditches on the far right side of the screen, and it flows from the oxidation ditches to the existing flocculated clarifiers and eventually the tertiary filters after. Now, given this land constraint, we decided to come up with a new plan view of the plant on the next slide. Everything in white is the existing plant as it sits. All the structures outlined in black are what we plan to include in the new BNR upgrades. Starting further south on the plan layout, there's a new influent pipe from the IPS that will be upsized to 24 inches to feed the splitter box that will split flow into 3 equal trains. There will also be a new RAS line, return activated sludge, that runs from the RASWise pump station at the back end of the process. Just north of the new splitter box, we're proposing a pre-anaerobic and anoxic structure. There'll be mixers located in all these zones. After the pre-anaerobic anoxic structure, flow will travel to the ditches, where we'll completely rehabilitate the existing along with build a third new one. The main overhaul of the ditches includes adding fine bubble diffusers at the bottom, fine bubble diffuser grids, as well as horizontal mixers. These are key because currently the plant is having problems with piping failures and settling. So we want to eliminate using air to provide the velocity in the ditches. That's 1 foot per second. So we're going to install horizontal mixers to provide that velocity. There's also going to be new nitrate recycle pumps for the 5-stage BardenPHO process. These are required to drive denitrification back to the anoxic zones in the 5-stage BardenPHO process. Flow leaves the ditches through a 24-inch pipes, enters the post-anoxic and re-aeration structure. There will be mixers located in the post-anoxic, but the re-aeration zones will have fine bubble diffusers as well, fed from the new blowers on the east side of the ditches. After the new post-anoxic and re-aeration structure, flow will travel to a clarifier distribution structure. Well, we'll be able to feed the existing lime and alum building. These will not be used in the design of the BNR process, but just in case we're having issues meeting that total nitrogen limit, the plant operators will have the ability to add those chemicals in case the BNR process isn't working correctly. So after the clarifier distribution structure, flow settles out in the flocculated clarifiers and eventually onto the post clarifier structure and the tertiary filters. We'll allow for future expansion to the filter galleries by including another gate with access to future filters. Moving on to the next slide, here's highlighted all of the scope of work for the project, mainly demolishing and rehabbing old structures, along with retrofitting blower area C to have VFD, variable frequency drive blowers. The new structure is highlighted by the third oxidation ditch, as well as a matching flocculated clarifier. We're also going to add the pre-anaerobic anoxic structures and post-anoxic reaeration structures. We'll also need a new sludge pump station for the increased sludge production that the plant will have. They'll be using most of their dewatering process and sludge. They currently just truck that out from the plant for land application. We're not going to be designing, that's outside of our scope for this project. On the next slide is a list of process equipment. I spoke to most of these during the plan layout. The only additional is the SCADA INC instrumentation controls equipment that we're going to provide for operators. This will allow them to finely tune the BNR process and ensure that they're meeting their new 3 milligrams per liter TN limit. And on the next slide, we're going to have Savannah go over construction sequencing for this project, as temporary operations are crucial for this plant. They cannot reroute any wastewater to neighboring facilities.
Yeah, so like Drew said, it's essential to have 2 of the oxidation ditches and their associated clarifiers online while we're constructing and rehabbing the others. So we're breaking the construction down into 3 phases. The first phase, which is shown by the green icons on this aerial view, will be new construction. So we will build the new oxidation ditch and its clarifier, along with the post-anoxic and reaeration structure and pre-anaerobic anoxic structure. The second phase will be taking down one of the existing oxidation ditches highlighted in blue here and rehabbing that ditch while temporarily piping the flow associated with that ditch to the newly built train. We'll rehab that ditch and build some other structures. In phase 3, we will take down the other existing oxidation ditch, rehab it, and build the RASWAS pump station and the clarifier effluent structure. In our project, we also looked at the sustainability using the ENVISION rating software, which evaluates the project sustainability based on 5 criteria listed here at the bottom of the graph. And as you can see, our project rated very sustainable in almost all the criteria, which is green. Except it could be rated a bit higher in climate or resource allocation. So some things to address that could be using renewable energy or locally sourced materials. We also performed a preliminary level cost analysis as shown on this slide here. So we considered all of the process additions and constructions as shown in the top of the table, and we're able to determine an adjusted opinion of cost at about $30.25 million. We also determined an annual operation and maintenance at just over $1 million. And that total project cost is in 2022 dollars and was adjusted for inflation. Finally, we do have some recommended upgrades that are outside of the scope of our work that we just want to hit on. We'll have to upgrade other parts of the plant to design for that new 6 MGD flow. So that'll include some of the preliminary treatments, such as the dual bar screen, grit removal, and some of the tertiary treatment like the filters and the chlorine contact chamber. Of course, we'll also have to plan for permits, such as the plan of approval for construction, authorization to construct, and making sure we keep in mind those new NPDES permits. So thank you very much for listening to our presentation, and we hope that our PER is able to answer any questions that you may have.